Okay, 2017 paper, question 11. A student makes the following statements about waves from coherent sources. And which of the statements are correct? So waves from coherent sources have the same velocity. That is correct. Waves from coherent sources have the same wavelength. Yes, because when they overlap, they can cause constructive or destructive interference. So they have to have the same wavelength to be able to overlap. And waves from coherent sources have a constant phase relationship. That is the definition of coherent sources. So all three of those are correct. So E is the correct answer there. Number 12. A ray of red light passes from a liquid to a transparent solid. The solid and the liquid have the same refractive index for this light. So that means the refractive index does not change. Which row in the table shows what happens to the speed and the wavelength of the light as it passes from liquid into the solid? If they have the exact same refractive index, then it's like they're not passing into a different material at all. So it's like if they were going from water to water. So there would be no change at all for either of those. So E is the correct answer there because the change in refractive index is the thing that changes the wavelength or the speed. Number 13. A ray of blue light passes from air into a transparent block as shown. The speed of this light in the block is. So we know the ratio of the speeds, and we know that the ratio of the sines of the angles are related in some way. So we know that Snell's law is n2 over n1 equals sine theta 1 over sine theta 2. We also know that that is equal to the speed in medium 1 divided by the speed in medium 2. We don't have any refractive indexes here, but we do have at the angles that we require. So the sine of theta 1, that is our theta 1. Remember, it's between the normal and the ray. That's our theta 2. Speed 1 is the speed of light in air, and speed 2 is what we want to find. So sine of 60 divided by sine of 40 is equal to speed 1, speed of light in air, 3 times 10 to the 8, divided by speed of 2. So if you ever think you haven't been given enough information, you're probably likely to be expected to use something that you already know or something that you remember. Best ways to rearrange this, I find, is flip them both over. So sine 40 over sine 60 equals V2 over 3 times 10 to the 8. So V2 is going to be sine 40 over sine 60 times by 3 times 10 to the 8. And that comes to 2.23 times 10 to the 8 meters per second. So D. Number 14. A student carries out an experiment to investigate how irradiance varies with distance. You guys have done this experiment. A small lamp is placed at a distance D away from a light meter. The irradiance I at this distance is displayed on the meter. This measurement is repeated for a range of different distances, and the student uses these results to produce the graph shown. The graph indicates, because it's not going through the origin, that there is a systematic uncertainty in this experiment. Which of the following will most likely to reduce the systematic uncertainty in this experiment? Now remember, systematic uncertainty comes from a measurement technique or the design of the experiment. So really what you want to do is something that will cause the biggest improvement in this experiment. And repeating doesn't get rid of your systematic uncertainties. It's something to do with the actual experiment itself. So the thing that you would need to change is basically the background light. So repeating the experiment in a darkened room is the thing that's most likely to get rid of the systematic uncertainty. So D. Increasing the range of distances isn't changing your experiment at all, really. It's just changing how many repeats you do it or how many times you do it, how many different distances you do it from. Replacing a small lamp with a larger lamp or decreasing the brightness of the lamp. Well, decreasing the brightness wouldn't help really much at all because your light would be even less bright. And replacing a small lamp with a larger lamp wouldn't really change the experiment much. You've still got a lamp. So really what you want to do is get rid of the background light. 15. Related to that, a point source of light is 8 meters away from a surface. The irradiance due to that point source at the surface is 50 milliwatts per meter squared. The point source is now moved to a distance of 12 meters from the surface. The irradiance due to the point source at the surface is now. So this is your I1 d1 squared equals I2 d2 squared. So you can leave it in 50 milliwatts per meter squared because as long as your answer is in that at the end, it's a ratio, so it shouldn't matter. So I1, first of all, is 50 milliwatts per meter squared times by d1 squared. So d1, the initial distance is 8, so 8 squared equals I2, which you want to find, times by d2 squared. The second distance is 12 squared. So I2 is going to be 50 times 8 times 8 squared divided by 12 squared. And that comes to 22.2 milliwatts per meter squared. So A for that one. And number 20, because we're skipping out some of them that you haven't quite done the theory for. This is one of those ones where it's an equation that you haven't seen yet, but you should be able, but you've got everything that you need to answer it. So astronomers use the following relationship to determine distance d to a star. Now this is advanced higher equation, but it's quite a nice equation. For a particular star, the following measurements are recorded. Based on this information, the distance to the star is. So we've got that equation, F equals L over 4 pi d squared. So F is the apparent brightness, which is 4.4 times 10 to the minus 10 watts per meter squared. L is the luminosity, which is 6.1 times 10 to the 30 watts over 4 pi times by distance squared, which is what we want to find. So the best way to rearrange that is distance squared is going to be 6.1 times 10 to the 30 divided by 4 pi times 4.4 times 10 to the minus 10. So really the only difficult thing here is putting it into your calculator correctly. You end up with a d squared to be 1.1 times 10 to the 39. Now, bear in mind that is one of the answers in the multiple choice because a lot of people will see that and go, right, I've got the answer, but you do have to square root it to get your distance. So that comes to 3.32 times 10 to the 19 meters, so A.